Go. Okay, perfect. So let's make it a bit bigger. Chain rule. First of all, I gave you something that is not ugly, something that is more like cute. And in here, again, you're gonna help me. I hope that today I'm gonna do a little better, but well, we never know. So the derivative that I got here is, okay, I got 1 plus, 2 pluses. Yeah, well, at least something, right? Let's move on. Okay. Wait for it. Perfect. So the logarithm is an outer function in this case. Then we have a square root, and then thanks God we have nothing else. So technically inside it's not just x but x plus 1, but the derivative will be just 1. So we go with a fraction of 1 over the square root of x plus 1, and then times the derivative of the square root itself, so that will also result in a fraction of 1 over 2 square root of x plus 1, and that's it. So in here you could keep the second part, as I told you many times. A bit different, you could just write 1 over 2 times x plus 1 to the power of minus 1 over 2. Okay, so give me pluses here. Okay, cool, thank you. Moving on, and then this is a product, right? So we are supposed to use both product rule and chain rule, though not so much of a chain rule. We have first part that is 2x, and the second part that is e to the power of x plus 1. So we're ending up with the derivative of the first part is 2, then e to the power of x plus 1, then plus the derivative of the second part, that's just gonna be e to the power of x plus 1, and we don't have any coefficient with x, so we don't have to multiply it by any other derivative, though we have to still multiply it by 2x, so I'm going to write it like that. Good? Good. Surprise. Okay, so this is a function that is slightly uglier. So the first, we're having a fraction. I'm gonna copy this one and input it here. So we're having a fraction of 1 over 2 square root e to the power of x plus, no, amazing, square root e to the power of x plus 1 over 2 x squared, and that's the derivative of a square root considering everything that is inside as a function. Then we have to multiply by the derivative of the inner function. The inner function in this case is the whole thing, e to the power of x plus 1 over 2 x squared. So the derivative will be our favorite, first of all, that's e to the power of x. Okay, plus this is also not that bad, just x, because we were supposed to do 1 over 2 times 2x. Okay, I got 1 plus. Good. 5. I got the third plus. How beautiful. 5. Then here, you should get used to this functional form for economic growth and so on. So here the outer function is a power, and the exponent is 1 minus alpha over alpha. Well, it is what it is. What can we do? So 1 minus alpha over alpha. We keep it like that. Then we multiply it by, let's do times, by the whole thing to the power of 1 minus alpha over alpha minus 1. So, no, don't. X to the power of alpha plus 1 and then up. And what is the fraction that we get here? Yes, so we just do 1 minus alpha over alpha, and then we have to subtract 1, which is just alpha over alpha, and that's what we get. So 1 minus 2 alpha over alpha. Lucas, you have Greek letters. You're the only one. Well, not the only one. You are actually able to type alpha. That's cool. Great. So that was the derivative of the outer function. So the exponent that is a bit weird in this case. And we have to multiply it by the derivative of the inner function, x to the power of alpha plus 1, and that will be just alpha x to the power of alpha minus 1. So here, what can we do? Can we do something? No, not even simplification. That's how it's going to look. Okay, and now the last one. So this thing is, let me rewrite it first for the sake of clarity. X to the power of beta. Alpha can cancel out. Yeah, well, yeah, that one. Yeah. Not that great anyways. But we can get rid of the denominator, which is good. I agree. Good point. So here what we have is x to the power of beta plus beta. I agree. For the sake of simplification, we can get rid of the denominator. Sometimes it helps. When especially you have 100 more steps ahead of you. So the exponent here was a fraction of beta over alpha. Okay, so that is just rewriting the thing. And now the derivative will be better. So I can see that what I'm supposed to do is beta, so over alpha. This is just my exponent, and I put it as a coefficient now, times what's this fraction? That's gonna be to the power of, and here we do beta over alpha minus alpha over alpha, and we get a fraction of beta minus alpha over alpha. So let me just make it a little bigger, because we have this things that maybe don't show correct. Okay, so now we can see actually all these little letters. Very beautiful. And that was just the derivative of the outer function, so the exponent. Now what we have to do is multiply this whole thing by the derivative of the inner function, so that's just beta x to the power of beta minus 1. Okay, beautiful, I have a plus and many pluses. Whoa, I nailed the chain rule. Okay, perfect. Now implicit function rule. So implicit function rule. Okay, first of all, we have the nicest thing ever, just x, y with exponents. So we remember that to find y over y prime x, so the derivative of y with respect to x, if we have just the relation between two. So to do that, we can write a fraction of f prime x over f prime y. Okay, so in our, this is even before the first one. So in our first example, f has the form of x squared plus 2xy plus y squared, and this is with minus, yeah, just a second, ms squared, yes, perfect. Here I forgot the minus. In the inverse function rule we don't have this minus, in the implicit function rule we do have this minus. So this is just Newton's binomial, the second, the square. But we don't care absolutely, it could be whatever. Then we can just use the rule and we get y prime, what was I doing? X equals to minus fraction. And here it is 2x plus y over 2y plus x with 2. Like this, everything with 2. Yes, equals 4 as in the equation is incomplete. Well, here what I wanted to take straight is the functional form. So I told you last time that our goal is to put everything to one side. Yeah, the answer will be the same. So our goal is to put all the variables x, y to left hand side, for example, or to right hand side, and then call this a function f. And the constants, no matter the value of them, they will absolutely have no meaning. So I could technically here write minus 4, right? To be like absolutely rigorous, but we know that the derivative of the constant is 0, so really we don't care. And it shows very nicely in the number 4. I will show you like actually why and what for, and for the sake of what we do all that. So this will be the answer for the first one. For the second one, beta, sorry, why on the second term of exercise 6, second term, beta minus 1 over alpha. Okay, so this is my favorite mistake, and look, so we had beta over alpha minus 1. minus 1. So that equals to beta over alpha minus, what is 1? It is alpha over alpha. So we cannot do the subtraction or sum of two fractions if they don't have the same denominator. So now we reduced it all to the same denominator, alpha, and we can write the numerator now as, well, beta minus alpha. Yes, but this is a good point because obviously you all know how to deal with fractions, right? But for some reason here we all make mistakes. And now I remember, as you asked me, I remember that I was making the same. And you have to be very careful because this is the last thing that you think of when you have a monstrous utility function and you have to not only take the derivatives but then move on to optimization, and you are like, okay, fractions, and then you don't pay enough attention. So this is a good point to raise, so you pay attention to everything. Great, so for the second implicit function rule example, I am going to write it like this. So it's going to be a fraction of 2x minus y squared, y plus x to the power of e. Okay. Great, so it's much worse in terms of the implicit function derivative now, because we'll have to deal again with 4th floors fractions, but well, to train your attention to details, you know. Okay, so first of all we have a minus, then we have a fraction, and now in the numerator we're supposed to write the derivative of this thing with respect to x. We have to use now the quotient rule, so this is a fraction that we cannot simplify, so let's do it. We're gonna have a fraction, so what about the 1? Yeah, 1, the derivative of 1 with respect to both x and y will anyways be equal to 0. We could write it or not write it, it does not matter. And usually the constants, we just omit them to not even think of them, because we know that their derivative will be 0, like whatever. Perfect. So if we had, for example, here on the right side, not 1 but x, yes, we were supposed to move it to the left and then consider it x, right? So, okay, now we're taking the derivative, and the first thing that we all do is always squaring the denominator. So here it will result in a exponent 2e. Okay, now the derivative of the numerator, which is 2 with respect to x, we multiply by the denominator, which is this thing to the power of e. Then we do minus the derivative of the numerator. No, the derivative of the denominator now with respect to x, that will be e y plus x to the power e minus 1. Okay, bigger. Perfect. Great, so we're done with the numerator. This was supposed to be a derivative of this function with respect to x. Now the denominator, the derivative of this function with respect to y. So that's going to be a fraction again, because it's the same problem that we're having here. And the denominator of this function, of this fraction, will be exactly the same as if we were doing it with respect to x, because they're like both there. And the derivative of the numerator now with respect to y is minus 2y. We multiply it by the denominator, I'm just going to type it, to the power of e, then we do minus, and the derivative of the denominator with respect to y is symmetrical to the one with respect to x, and it will be e y plus x to the power of e minus 1. Okay, perfect. We can certainly simplify it because we have here and here the same thing. And we end up with something like the numerator of, like the first numerator divided by the second numerator. We forgot, yeah, I could forget. In the numerator of the numerator, it's this one. Wait, I'm getting there. Third line is this one. We were supposed to multiply the derivative of the denominator by the numerator. Yes, you're all right. Yes, it's just that. So I took the derivative of the denominator and I was very happy, and it was too long and I gave up. So yes, certainly we have to multiply it. We have to do it both we have to do it in both numerators now. 2x minus y squared. And here too. Okay, perfect. So yes, this was the derivative of a fraction, and for the first part it was simple because the derivative of the numerator was here 2, the derivative of the denominator, the denominator itself we just wrote, and then for the second part it is the derivative of the denominator times the numerator as it is always. So yeah, then you simplify it and you get something like, yeah, this is going to be really cool here because you can factor y plus x to the power of e minus 1 and then get whatever you get. Doesn't matter. For now, we are not doing algebra because we need to do a lot of other stuff, but you can train your algebra here. Cool. And the last one, finally, 3, f of x and y here was y to the power of x plus x to the power of y, y prime x is equal to, okay, so as always minus fraction, and the derivative of this thing with respect to x, right? So here we're getting a logarithm of base x y. Assuming y to the power of x is e to the power of, wait a second, assuming that y to the power of x is equal to e to the power of x logarithm y. Yes. I don't know. Does it make it much easier? Okay, let's go first with my my option, and then we can you can unmute yourself and explain how would it look with that. But just help me out here. The derivative, like we're taking it the way it is, right? So now when we're taking the derivative of this function with respect to x, we consider y as a constant. So for the first one, what we're getting is this, right? We're getting this log. Are we? No? Did you like my typo in the name? Well, I did. Okay, so the first main formula is here. So what we're doing is this one. Yeah, well, whatever I did, I don't know. we're using this formula for a prime x. So, okay, cool. Now we can up. So this is not, yeah, forget about that. We are ending up with y to the power of. Nah? But if we take y as a constant, why couldn't we just write it y times x to the power of y minus 1? For this part, obviously. But here, I'm just taking, for now, you're absolutely right, Elisa, for the derivative of the second term of the sum. But I'm just trying to deal with this for now. And I told you that this is the formula that you don't have to know. And since we don't have to know it, we can just go in our presentation and check what it is. Yes, and it's going to be y to the power of x logarithm of natural logarithm of y. And natural logarithm of y in this case will be a constant. Okay, cool. And then, of course, yx to the power of y minus 1. And the denominator. So now we're considering the derivative of this part with respect to y. So we consider x as a constant. This is just a nice exercise for you to switch. And here we're going to have xy to the power of x minus 1 plus x to the power of y natural log of x. Okay, and now let's listen to a smarter way to solve it. Yeah, Prodipto, you can unmute yourself. It's twice as long. Well, it's twice as long because first you, yeah.
It can be done, as I said, using if we use the logarithmic definition of function, expressing it as in terms of exponential. But it's very long. Yours is very short. It just takes 2 steps.
Yes, well,
unnecessarily long.
Yeah, okay, but you're right. I agree. So if you're feeling comfortable with the...
What I wanted to avoid was basically having 2 variables, as in one in the exponent and one as a base. I wanted both of them on the same line. If I take a log, so I'll have ln y multiplied by x or ln x multiplied by y. I can change them easily. That's what I think, but it's a much longer method.
Okay, well, you avoided using this, right? Yeah. Okay, well, that's good. But I'm assuring you, you're not gonna see this stuff. You could simplify the y and x in the end. Yeah, I could simplify many things, but I don't want now. You're right. So you're not gonna see something like that. You're gonna see max that you can see for yeah, max that you can see with the the variable in the exponent is e to the power of x. I told you this formula, you don't need it, so you don't need it. But just for the homework, I decided to give it to you to train your switching from, okay, what is the variable, what is a constant? And you had your presentation and you can use the formula. So that's the result. And finally, we're gonna see now why do we need it and what is it all about and what for. Okay, so for this last one, it's all good or no? Time to ask questions. Okay, I see that it seems to be all good. Perfect. So, now consider a production function. So let's put it right here. Consider a production function Q of K and L. So we have a production function. Our two inputs are capital and labor. Very standard functional form as well. So a to the power of L, AL to the power of alpha, K to the power of beta, up, okay, great. So this is the function that you will see the very first class of economic growth, and alpha and beta usually are less than 1, but for now we don't. Do we need it for now? No, we don't need it, not even for the simplification part. So alpha and beta are just whatever constants. They can take whichever values, and a nice case of Cobb-Douglas function, because this is Cobb-Douglas function, is when alpha plus beta gives us 1. But well, in here I don't need it, we don't think about it. So we are like, for any fixed level of Q, find the derivative of K with respect to L. So what does it mean for any fixed level of Q? For the utility function, we already saw a little bit that we can have indifference curves, right? So we're saying all along the curve, the utility is the same. So we change the amount of goods, like adding 1 and subtracting another 1, and we stay at the same level of utility. We can use different combinations to get the same level of utility. The same thing happens with the production function. We can have different combinations of the input, labor, capital, and still get the same level of production. If, for example, our industry is heavily labor, well, substituting 1 person might require us to add 2 more machines to actually reach the same level of production. But again, you'll see it, and this is just a simple logic of what is fixed level of Q. So let's say, well, we're now having something like Q0, and this Q0 is equal to this thing. And you see now, and we saw it before with the implicit function, that whichever level of Q I put here, 1, 2, 3, 400, 300, 3000, the derivatives and the implicit function rule will work the same, right? So the constant doesn't matter. So we don't even have to add this step. We can just start straight from, okay, we have a production function of 2 variables, and we can actually, for a given whichever level of Q, find K prime L. So how do we find it? Well, it's going to be a negative fraction of the derivative of this thing with respect to, I don't know where I did it. The derivative of this thing with respect to L, so Q prime L over q prime k. Okay, well, the derivative of the q function with respect to L, like this stuff we're taking here, will be a alpha L power alpha minus 1, because I'm just considering now k as a constant. So for me it works like a coefficient, so the only thing I had to do is to derive L to the power of alpha, and alpha is constant. Then for k it will be absolutely the same, symmetrical, not absolutely the same but symmetrical, and here we're gonna have how we got the division. Which division? This is just coming from the implicit function rule. The derivative of k with respect to L is equal to the derivative of the q function with respect to L over, it's like this. So what we did is just changed letters. Is that okay? Okay, cool, yeah. So I'm already using the implicit function rule for this functional form. Beta minus 1, so up times L to the power of alpha. Okay, so look what we did. It looks too symmetrical, so it can be confusing, but anyways, that numerator is the derivative of the q with respect to L, the derivative of this function with respect to L, so we consider k as a fixed constant, and a is a fixed constant since the very beginning. Yeah, I didn't say it, but a is a fixed constant since the very beginning. It's just a technological term, let's say, or whatever it is. So cool. This is what we get. And here what I'd like to do is simplify it actually. So before we discuss what's that and blah, blah, blah. So the way we simplify it, well, a and a go away. Then we have here alpha. Here we have beta. We cannot do much with that. And now let's see what do we have in the in terms of the exponents, because see, you have here L to the power alpha minus 1, L to the power alpha. So what I can do is to, for example, group capital in the numerator and the labor in the denominator. So for the capital, now the exponent will be beta. Minus beta minus 1. What happened here? Well, just working with fractions, working with exponents. What I had is k to the power of beta divided by k to the power of beta minus 1, and we know that if we do the division, we have to subtract exponents. That's going to be the exponent of k, and the exponent of L is going to be absolutely the same, except for we're having alpha, and for the L it makes sense to do it here. So alpha. Cool. So look, here I had k to the power of beta, and then I just did the division. And then for the L, I also did the same. So when I have this L here and this L here, what I can do is to move L back to the denominator, not back, but move this L to the power of alpha minus 1 to the denominator, and you know that that will mean doing the negative of the exponent, and that's what we have. So this is not it, because here you can see how beautifully it it turns into a fraction of alpha over beta k L. Because you calculate here the exponents and you get beta minus beta plus 1, alpha minus alpha plus 1, so you end up with 1. Okay, so this is beautiful. And this is something that you will do many times. So the worst case scenario for your economic growth class, you don't remember, don't know what's happening, what's the implicit function. Just memorize this framework, you'll get 1/4 of your answers done. No, I'm kidding, obviously, don't memorize it. You have to understand. Great, so what is it? What is K prime L? So it's cool. Now we see, okay, we can, we know the production function. We see that this is the capital, this is the labor, and if we start at a point where we have 2 units of labor and 1 unit of capital, well, we substitute it here and we actually get the value for how many units of capital we need to add if we give up 1 unit of labor. Or, well, how many units of capital we can give up if we add 1 unit of labor. Okay, so great. And for the 5th, we have absolutely the same idea, right? So what will be the economic interpretation of y prime x if x and y represent the amounts of 2 goods entering a utility function y of xy equals 2x plus 3y. We calculate y prime x. This is just something that finally looks not that scary. We get 2 over 3. So first of all, so 2 over 3 works. Well, minus 2 over 3, right? And now tell me, how do we call the goods if the utility function has this form? Perfect substitutes. So perfect, yes. I'm going to talk about that right now. So first of all, the economic interpretation of y prime x will be the MRS, so marginal rate of substitution of y by x. So the way we should understand it is how many units of y we can give up if we add 1 unit of x to stay at the same utility level. This is very realistic when you are at the store and you like oranges and apples both the same. You kind of feel like, okay, I see that the price of oranges is greater, so I want to buy just apples. So how many apples do you have to buy if you, for example, give up 1 orange? You know, so that's understandable from the economic point of view, and you now see how you calculate it. And it is super important. There you will see that this will actually equal to the ratio of prices of the goods and so on and so forth. For now, don't think about it. I'm just giving it, writing it down here so you're getting used to it. Don't think about prices because we have to prove it also and so on. But, well, this is going to be the implicit function rule in action in our economics. So we'll use it in micro, in macro, in economic growth, and maybe no, not in econometrics. So this is something important, right? So now we know it, we can move on. That might not make sense, but could you do an example for MRTS, like with oranges and apples? Well, I tried. So you are now running a factory and you're producing 100. What are you producing? 100 pairs of shoes. And what you use? 100 Ferraris. yeah, what do you use? You use labor, so people, and capital, machines. So you are like, I like producing 100 Ferraris, but don't like these workers much. They're loud and they ask me for wage increase. So you're like, how many machines do I have to buy to substitute this annoying worker? So you're like, my goal is, for example, fire one of them, the worst, the most annoying. So how many machines do I have to buy now to stay at the same level of production of 100 Ferraris? Does it make sense? You're welcome. Okay, great. So now we have to do the inverse. And we're not going on a break before you all tell me, I understand. We're gonna take the same example. So I need you to focus again. Don't ask me many questions for now. Oh, what's that? So we're gonna take the same example. We have a function y equals to f of x. So y is a function of x right now, and the functional form is x cubed plus 1. Now we want a derivative of x with respect to y. So let's think. The simplest will be, we have a demand like quantity in terms of price. So if we get the derivative of quantity with respect to price, we get the rate of change of demand, right? But we can also require for some reason the opposite derivative, so the rate of change of price with respect to quantity. So that is the idea here, right? So we can want a derivative of x with respect to y just because we needed to draw some conclusions. So when you're given a function y in terms of x, you can easily find a derivative of y with respect to x just using our rules. But what if you want the opposite, the other way around, for whatever reason? So let's fix it here. We want a derivative of x with respect to y for whatever reason. Because we know that y prime x is change of y when x changes by something, right? Well, let's say by 1. And the x prime y is change of x when y changes by 1. Okay, so first of all, we have to make sure that the function exists. So the function x in terms of y exists. So we're actually able to get this derivative, right? So that is making sure that the inverse of y exists. Okay, so for this exact example, it does exist because this is a one-to-one mapping, and now you all know how to actually make sure that it is a one-to-one mapping without even plotting it. Perfect. So I trust you all took your time to consider the link that Walid sent us yesterday. Sorry. Up. Okay, so now ways to do it. And the first one is something that will seem very logical to you and it will make perfect sense. Well, there are two steps. Find an inverse, differentiate it. Differentiate it, so find the first derivative. Okay, so find an inverse. In this case, will be x expressed in terms of y. Okay, so let's first do this. So we know that it will work for sure. Well, we wanted the derivative of x with respect to y. Well, let's express x in terms of y and get our derivative. So here, to get an inverse, what do we do? Let's just do this expressing x in terms of y. So our first step. There are two ways to do it. Okay. Way one. So that's way one. Find an inverse and differentiate it. And now we're gonna do it. So let's express x in terms of y. We had y equals x cubed plus 1. Okay, so we know that y minus 1 equals x cubed because we just moved 1 to the left. Now we know that x cubed here, what we have to do to extract x, we just have to take cubic root of both sides. So here y minus 1, and that has to be equal to x because we took cubic root out of both sides. Okay, so I see a lot of pluses, so I hope that getting an inverse is not such a big deal for you anymore. Obviously, if a function is not like monstrous, right? Here we had just 2 steps. Okay, perfect, but you're not gonna have anything more difficult than that. Great, so let me actually put it in a functional form already. So x of y equals this. Perfect. That was the first step. That was easy. Now, let's differentiate it. Let's take the derivative of this with respect to y, because now we have all means to do it. And in order to make it even simpler for us, I can rewrite it like this. No. Like this. 1/3. Perfect. So, let's derive it. X prime y is equal to 1/3 do you agree with this derivative? Okay. More. So we could also write. I just want to make sure because this is super important right now. I need you to understand me at every step of this stuff. What I wrote is the same as this. Okay, so if you got it like that, because before I was always telling you, you don't have to do anything with the negative function, so this is going to be your answer. Okay, perfect, great. So this is the same as this. This fraction of the fraction in the exponent just tells us that it can be written in a form of a root. Well, in here it's a cubic root. And the negative just means that the thing goes in the denominator. Okay, perfect. So let's highlight this. Okay, this is going to be useful. Perfect. So that was way 1. And this way should make sense to you, right? Like, if you didn't get what I was trying to desperately explain, but the formula isn't holding. Y prime x is equal to, well, first of all, y prime x, I mean, the formula, which formula? Wait a second. Don't confuse us just yet. I had a question to everybody. I'll show you that the formula is holding. Swear. I got it all here. First question. For those of you who didn't get it yesterday, maybe for everybody, does this way make sense to you? So if I depart with, I want a derivative of x with respect to y, does this make sense? So, okay, I get y, x expressed in terms of y, and then I get a derivative. This makes sense. Okay, great. And this is an easier way to do it than way number 2. So, way 2. Don't ask questions, just keep. Use the inverse function rule. So, first, find y prime x. Second, apply the formula. So the formula, you remember y prime x is equal to 1 over x prime y, or the other way around also works. X prime y is equal to a fraction of 1 over y prime x. So first we find it, then we apply the formula, and there is the third step that we did not, well, I showed it, but it was too messy. Replace x with its expression in terms of y. So in other words, with the inverse function. Okay, let's do it following this way number 2. So get ready to see some magic. First, we know that y in terms of x is equal to x cubed plus 1. This was the function that I gave you in the beginning, and this is something that you should tell me, stop asking stupid questions. We already know how to find this derivative. That's how you find this derivative, right? So that's going to be the derivative of y with respect to x, and obviously we get it in terms of x. Now, apply the formula. Well, okay. Let's apply the formula. So, x prime y is going to be equal to a fraction of 1 over 3x squared. Well, okay, we applied the formula. We just substituted in the denominator y prime x with its expression. But then here is where the magic starts. So this is not just x here. This is x of y squared. Now we say that this is our third step. Replace x with its expression in terms of y. And so let's replace it. We already got the inverse here. It was the first step here, so we got it. This is the inverse. Okay. So fraction 1 over 3. Now I'm going to write it. How should I write it? So instead of x, right, we write the function of x in terms of y, and it was supposed to be squared later on. So the expression is the cubic root of y minus 1, and if we square it, well, we're gonna get we're gonna get y minus 1 and squared, right? Because, well, for it to be a little clearer, we can just do it like that. Okay, perfect. So how did we just now get this expression? Well, we took the inverse function rule and then we just substituted x with its inverse that we already had because we got it. And this is the magic. So both ways work. You get exactly the same value for the derivative. So the thing is, even if you use this way too, you have to find an inverse. You cannot find the final answer, so the derivative of x with respect to y in terms of y, you cannot get it. There is no minus here. This is not even minus. Okay, you cannot get it without finding this expression of the inverse. And certainly this way too might be too long, might be not the optimal way to get it. This actually just depends on the function. So sometimes finding the derivative of the inverse, so if you first find an inverse and then find its derivative, sometimes it's just too difficult. So sometimes it's actually making sense to do this. But, well, I'm not advocating this way to find the derivative. I'm not saying that if you have this setup since the beginning, right, if you just have to find the derivative of x with respect to y given y with respect to x, you should totally do this and apply the inverse function rule. No. I wanted to show you that it works. I wanted to show you that you actually get the same result. And we're going to check for another example from the classwork. And I'll show you that it also works again. So for the second lecture example, it will give us the same result. And I think in that case, no. In both of the cases, in this one that I just showed and in the second that I will show, that is just an example from the previous lecture, it is much simpler to go like that and get your expression. But, this works the second way too. Yes, you may, Lucas, ask something for the first way. If you want to unmute, you can.
I think in the two ways have something very similar. The first step, which is find an inverse x expressed in terms of y, and third step, it's quite the same. It's identical. I think that is, regardless the ways, I think that's the first step, no matter the way we have to do that. So the first way, I suppose, is the second step, and I may add, actually, it's not differentiate, it's derive it, because it's a different things. The the differentials is much more for sensitivity analysis and something like that. The derivation is something else. That's for mine. That's for
Yes. Thank you. Thank you. You're right. Yes. I'm mute.
Can you hear me?
Yes.
Hello? Yeah, I'm very sorry. Just one question. In the way one, we transformed what we got out, like what we did in step two. We just transformed it into one divided by like the left side. Yes, we just changed it, right? And in way two, can we go down? We just put the derivation into the x of y.
Instead of x of y, we just throw.
Over 3.
Yeah. This is
Like, why can we just put like, I mean, in step 2 and way 1, we just transformed it into 1 divided by the stuff. Don't we have to put all the 1 divided by the stuff into x of y? Do you understand what I mean? Like, it's kind of confusing me. I think you don't understand what I mean, right?
no. I'm trying. So shouldn't I have 1 over here?
Yeah, like, shouldn't we put the whole yellow thing in step 2 of way 1 in it?
No, because we're replacing x of y with just the function, with this. We already found the derivative. We don't have to replace it with its derivative. So what we're doing here is just writing an inverse instead of this. An inverse that we found here.
Yeah. Okay, I'm so sorry. Okay, I got it. Okay.
Perfect, because otherwise you're doing double derivation.
Yeah, this was my mistake. Okay, I'm sorry. Thank you.
Yes. Okay, the unmute session. Go ahead.
Yeah, I'm slightly confused as well. I've understood both the ways. Way1 is perfect, way2 is fine as well. It's just that we've been given a function in way1 or way2. Either we're doing an inverse and then differentiating, or we're differentiating and then finding the inverse. I just have one question. In way2, we are using the formula xy prime is equal to 1 by yx prime. We are actually assuming it. Is there any way to rigorously prove this formula with an example?
You mean with an example or in general? Because with an example, that's just what I did.
Okay. In the second way, we have xy prime is equal to 1 by 3 to the power 2 by 3 y minus 1. If we inverse that, we should be getting yx prime. Yes, but yx prime is 3x squared.
Oh, yes. So what's the problem?
One second. So we have two different variables in yx prime and xy prime.
Y prime x is supposed to be in terms of x, and x prime y is supposed to be in terms of y.
Just to clarify, both they won't be in terms of one variable. It's not possible, right?
Okay. It is not the same variable. So what you can find in some literature is actually both of them using x, but that is just because the inverse is expressed in terms of x again. So remember I showed you in the beginning, like, this is the correct mathematical notation. Like, we could have x here still, but just meaning and having in mind that it is already x, an argument of an inverse function. So it looks clearer when we have two letters, because yes, we just get an inverse by expressing x in terms of y, and well, x prime y is supposed to be in terms of y. But yes, you can read something with the same variable, and you just have to understand that it's an argument not of the initial function but of the inverse function.
Thank you so much.
You're welcome. Okay, so now do you mind putting pluses in the conversation if this is making more sense than what I was trying to desperately prove yesterday? Okay, this is better, right? I'm glad. So I'm going to now download this note in PDF, and I will send it your way as well. And I'm glad that we found a way to go step by step through it. I really want to show you the lecture example as well, but that will be fast. Okay, so now we're gonna go on the break, and it's gonna be a 10 minutes break. So we're back on at 31. Okay, and I'm going to quickly show you the example of the lecture, just one of them, and we're moving on.